Morning and welcome to this video from 2015 physics sample paper. You can see the video is from class 12 physics. I have picked this from CBSE website, and as usual I'm doing case study. Now the good thing about case study, it teaches you a lot about the concept and is a quick revision of the whole topic. Okay, it's a practical application of what you have learned in theory. Now let's study this question. Dimpi's class was shown a video on effects of magnetic field on current carrying straight conductor. Okay, so there is a video which was shown to Dimpi on the effects of magnetic field on a current carrying conductor, which means a current carrying conductor is lying inside a magnetic field. She noticed that the force on the straight current carrying conductor becomes zero when it is oriented parallel to the magnetic field, and this force becomes maximum when it is perpendicular to the field. All right, so what Dimpi notices is that there are two forces. One, which is minimum force when the conductor becomes parallel to the magnetic field means B, and the force becomes very high when the current carrying conductor becomes perpendicular to B. She shared this interesting information with her grandfather in the evening. Then she goes back to the home and she tells her grandfather, I have seen this experiment where I saw two types of forces on a current carrying conductor when we change the alignment of the current carrying conductor with the magnetic field. He explained to Dimpi that similar things happen in real life too. When we align and orient our thinking and actions in an adaptive and accommodating way, our life becomes more peaceful and happy. So the grandfather tells that, in real life also you will find physics-like situations where if you become flexible, I mean, the word used is flexible by me. The word used by the grandfather is adoptive and accommodating, but I'm using the word flexible. If you become flexible, the life becomes very peaceful. I mean, whatever direction you have, you just align with the direction of that trend or whatever is happening around you. The life will become very peaceful. If you go against it, people will apply pressure on you, people will apply force on you, and you will feel bad about it, right? This is what he meant. However, when we adopt an unaccommodating and stubborn attitude, life becomes troubled and miserable. So we should not be stubborn, we should be flexible. If you see, this is the message of the grandfather upon listening the experiment. We should therefore always be careful in our response to different situations in life and avoid unnecessary conflict. So grandfather says, depending on how you respond, life will give it back to you. If you respond in a very stubborn like attitude, people will run away from you and people will be very harsh with you. But if you are flexible in your attitude and you accommodate other people's request, then people will like you and people and life will be very happy and peaceful for you. So obviously we are doing a physics chapter, but a lot of this question has to do with the values in life. So I thought maybe it's a good opportunity to discuss the values also, right? We must carry in life. And so let's go back to so there are two questions being asked. First is express the force acting on the straight current carrying conductor. This is the question, right? Express A. Look at the question. Express the force. You have to express the force acting on the straight current carrying conductor kept in magnetic field in the vector form. State the rule used to find the direction of this force. Let's do the question number 1. I hope the question is clear. Dimpi sees the videos that there is a magnetic field on a current carrying conductor, right? So what is the effect being referred to? The effect being referred to is the force, right? So a magnetic field applies force on the current carrying conductor. Okay, she noticed that so there are two types of forces that were noticed. One is zero, okay, when it is parallel. So zero and parallel, note the words. Then note the word maximum and perpendicular. All right, so if you look into this question, let me first tell you the theory and the concept behind this, And I'm sure you would have recognized that what this is all about, but for the purpose of a quick revision, I will not give you an answer, but an explanation. My channel is known for explanation, and perhaps the only channel in the country which is taking the trouble of explaining you. So you can see the solution in any app, any website, any portal, but you will not find an explanation the way I will explain it. My job is to make physics really easy for you and not complicated for you. Even if your exams are coming, you watch my videos. Probably if you keep NCRT with you and you watch my videos, the complete course can be revised. I have around 2000 videos. Okay, so let's go and understand the theory behind what happened and what type of effects happen when a current carrying conductor is kept in a magnetic field, and when the alignment or the direction of the current carrying field conductor keeps on changing inside the magnetic field. How does the force get impacted? Okay, all right, let me just show you a diagram. And mind you, my purpose is not to solve this problem. I can definitely solve this problem in one sentence. I know the formula, I know the answer, but you will not learn anything from that. My idea is that you should learn something from what I talk about. So I will explain you the this effect of the magnetic field on a current carrying conductor. So if you look into this diagram, this black color wire which you see, right, this black color wire is the current carrying conductor, this one, right? And if you see the white arrow, which you can see, I'm sure you can see the white arrow, this white arrow is the current in the conductor, right? So the current carrying conductor has a current. So the black is the wire and the white arrow is the current. All right. If you look into the diagram, what I've done is the magnetic field has been drawn in a particular plane, right? In which the current carrying conductor, you see the current carrying conductor and the magnetic field, they're lying in a rectangle. So you can see this rectangle, right? This rectangle, this one, this is a rectangle I'm referring to. This is a plane. Now this could be an XY plane and this could be your origin, right? So this could be your origin, or this could be your X-axis, and this could be your maybe Z-axis. Let's call it Z-axis, which is coming outside the paper. All right. And what you have done is the magnetic field is in the XZ plane. So you can see the magnetic field, right? This is a B. B is the magnetic field. The green arrows are the magnetic field. It's a uniform magnetic field for this question. So you can see the spacing between the green arrows is almost equal, right? I mean, I've drawn it with my hands, so it may not look like that, but it is a uniform magnetic field. What is a non-uniform magnetic field? When the spacing between these lines is unequal. That is a non-uniform magnetic field. So point is, the wire, which is the black wire, and the current inside it, and the magnetic field shown in the green is in the XZ plane. They're lying, for example, they're lying on the ground, and the magnetic field and the current carrying conductor, right, they are making an angle theta. You can see this angle. I will just enlarge it. See this angle again, right? So you can see the direction of the magnetic field is in the x-axis. I have already shown you, right? This is the direction, and this is the direction of the current carrying conductor or the current. I will talk about something else also, but for the time being, let's say this is the direction of the current. So the angle actually is not between current and the magnetic field. The angle is between the wire. Note this word, that the angle you may believe is with the current. It is not with the current, it is with the wire. And I will tell you the difference very soon. Just wait for that, okay? So this angle is between what? It is the angle between the magnetic field B and the wire of length L. So the wire, which is a physical thing, you can touch the wire, right? That is the angle we have to consider. We don't need to consider the angle between the B magnetic field and the current. It is not the angle between B and I. It is the angle between B and L. This is what I am trying to tell you. But I will tell you what is L. L is the length of this conductor, right? It has a length also. We will draw all of this. I will show you the labeling of L. Don't worry. Now, if you see this particular arrangement in which the conductor and the current carrying conductor and the magnetic field make an angle theta, what is our result? What is the effect? The effect is that the conductor experiences an upward force in the y-axis maybe. Why y-axis? If you this is your x-axis, this is your z-axis, then y-axis is perpendicular to this plane, right? So this is y and this is your x and this is your z, right? It's a coordinate system, and you can see the plane in which the wire was there. The wire is somewhere here, right? The magnetic field is somewhere here. So the force is perpendicular to the plane xz. So this is your plane, right? This is your plane. This is your plane. And look at the direction of force. Force is acting. So the wire will tend to go up. Okay, the wire, which is a black color conductor, will experience a force upwards and will tend to go up. It will start going up. This is the effect being referred to. So if you keep a magnetic field, right, and you keep a wire with current of some length, that wire will experience a force which is going upward, right? It is going upward. The force is going upward. Just see that, okay? So this is the direction of the force being referred to. So this is the force I am referring to. I hope this is clear, right? Now, magnetic effect, this is called as a magnetic effect on the current carrying wire. So magnetic effects, the magnetic fields are very powerful. If they see that a current carrying wire is kept in them, then they start exerting a magnetic force on that current carrying conductor, and the current carrying conductor starts moving in a direction which is perpendicular to the plane of magnetic field and the current. So current and magnetic field are in the same plane. I hope this is making sense. All right. Now let's talk about what, I told you that I will tell you something special. See the expression, which is a vector form of the expression, the force which is experienced by the wire. Okay, let me write the expression for that. Okay, let me write the expression for that. What is the force being experienced by this wire? Let's write that, and let me then explain you the each part of it. So the way we write this is that the force which is experienced by the wire is given by I, the current in the conductor which you saw, the white arrow. Okay, then dl cross b. This is the expression, okay, vector form of the force experienced by a current carrying conductor of length. What is the length of this conductor? The length of this conductor is dl. And what is the current inside the conductor? I. What is this sign? Vector product. I have an excellent video that will help you understand the meaning of the vector product. Don't forget to watch it. It's fantastic. You will love it. Okay, it's very explained in a very lucid, in a very simple manner. So this is your vector product and this is your magnetic field. Okay. Now, what I'm trying to tell you is, so it's okay. See, between I, okay, between I and DL, students have confusion. One is the length of the conductor, which you saw, right? You saw this black color wire, okay? This black color wire you saw, right? Let's go back and see the black color wire. So you saw this black color wire, and this is a mystery I'm going to remove now from your mind. So this is the black color wire, and this is the what? This is the current which you saw inside the wire, right? So the what is the confusion? The confusion is, so one is the conductor has a length, right, which I have mentioned in the formula is dl. So even this wire, right, has a length. The good thing in this wire is that the direction of the current in this wire, you can see the direction of the current in this wire and the length, right, the current have the same direction. So whatever is the length in a particular angle, if you see the wire is making an angle theta, even the current is along the wire. There is no change in that. But generally, this is not the situation. The situation is something else generally, which I will just explain you now. This was done for making your life simple, right? But what is the general formula? The general formula will come to your mind now. See, if you see a vector product has two vectors in it, right? So you need two vectors at least to write a vector product. So let's say you write a vector which is A, right? And it is given by the vector product of B cross C. You have two vectors, right? You have a vector B and a vector C. Similarly, when you see a vector force, you need two vectors. Now, the confusion is, which is a vector? Is current a vector? Or length a vector? Or magnetic field a vector? The answer is, in this particular expression, length is a vector. Okay, so we will put vector sign on this. Current is not a vector. So the two vectors involved in the force vector, which is the force experienced by the wire when kept in the magnetic field, in this expression, the two vectors you have to choose are the length and the magnetic field. This is what I wanted to tell you. In this particular case, which we are studying, fortunately, the direction of the current and the direction of the wire, which is the conductor, is the same, right? And the length of the conductor, if you see the length of the conductor, this is the length of the conductor. You know, if I just draw more clearly, so this is my length. You can see the length, right? So it starts from O and it ends at maybe A, right? Let me just call it A. So OA is the length of the conductor, L. So they will give you this in the question expressed in meters. But the general expression we are studying, so a lot of students are confused between I and L. This angle theta which is there is between what and what? Is it between B and I, or is it between B and L? This is wrong. It is always between B and L. Remember that. This is very important expression. Okay. So now I will go back to the part A, answering part A. So the answer to this question is the vector form. Let me just show you the question. What was the question? Right, let's go back to the CBSE 2015 question. This is a quick revision for your board examination. It will help you revise if you have not studied this, right? And you will be able to see, if you have revised it, you will know how much preparation you have done. So you were supposed to find the vector form of the force, right? So we have written this expression. This is the vector form of the force which is experienced by the wire. Okay, this is the vector form of the force. Let me just enlarge it for you so that you can see it very, very clearly. Okay, this is it. And what is a force? It is always in newtons, right? This is always in newtons. Okay, current is in amperes. So the current length is in meter. B is in Tesla or Gauss, right? All right. Let me just tell you something more. Now, when you open this, so what happens? Where is the angle coming in this, right? The angle is coming in this expression when you open this particular expression. Let's open this expression and see what happens when we open this expression. Now, when you open this expression, it is equal to, so this is newtons, don't worry, this is Newton. Okay, so don't worry about it that what the hell is this. So this is a straightforward Newton. Now I'm opening this expression and this is equal to I dl and also because this is a small current, small part of the current carrying conductor, the force is also written as D. Small force is experienced by a small current carrying conductor. So this is the small force. This is a small length. Okay, I will draw the diagram of this small length also to help you understand the difference between I and DL, more difference. Obviously, this is small and this is small. If you have to find the complete force, you have to integrate, right? You go and watch my video on what is integration. Excellent explanation as to small, what is the meaning of the word integration. Also watch my video which is net change theorem. It talks about definite integration. I will put the links in this video so that you can go and watch video on what is integration, what is net change theorem, which is definite integration, and also I'll give you some more links. Go and watch them, you will love them. Anyway, let's open this. So this is magnitude of DL. Now we're writing the magnitude of DF. Okay, so whatever I'm writing is the magnitude of DF. The magnitude of DF is being written. Okay, so let's say it is, so I multiplied by DL multiplied by B into sine of angle between length and B. So theta is the angle between DL, the current carrying conductor, and B. Theta is not the angle between current and B. Don't assume this. This is the correct. So I will just rewrite it. What does it look like? We remember as B I D L, right? DL is, this is differential. This is also differential wala, right? This is DF into sine theta. So the answer is, the expression, the vector form was this. If you have to write the vector form, this is a correct form, right? Some people, if they don't want to write small force, they can also write this. I L cross B. Even this is right. If you don't want to write the small length, write this also. But since I'm explaining, I have written the very traditional form. You will get marks for both. You just need to write this is the complete force or the force. For when you use this particular expression, which I started with, write a small force acting on a small conductor. In this case, you can, even if you write this, you will not lose marks. You can write this also. This is also okay, right? So this is what we have seen right now. And if you go back to this question and you have to calculate the force when it is parallel and when it is perpendicular, right? So let's see the two situation, why it happens, okay? Why it happens the way it happens, and we will be able to relate to the expression. So if you see this particular situation in front of you, right? If you see this, so if you keep this wire, okay, let me shift the wire to, so first situation was the wire is kept parallel to the magnetic field, right? So I'm drawing this wire, I'm shifting this wire as a parallel wire. So you can see the new diagram, you will see something dark now, right? I'm drawing this and I'm shifting this wire. See, I'm not giving you the answer right away. I have already given you the answer of expression. I'm just giving you more explanation so that you learn this concept forever. You don't forget it, okay? So I will just shift the wire, and the idea is to tell you what is the impact of angle between the, so I've shifted this wire. Assume the same wire is now. So this particular wire, this wire which you see as a black wire is now here, okay? I have not made it as thick, but I can make it as thick also, right? So let me just make it as thick. So this is the wire now, and the wire is, this is the black current. What I've done, I have kept the wire parallel to the magnetic field. Same, right? The wire is also in the same direction. And if you remember what I told you, the current is inside this wire. I will draw the current also now, right? The white colored arrow in the wire. Okay, so let's do that. So let's draw the current in the wire. So the current has been drawn in the wire. This is the current, right? You can see the current. I will just enlarge it. Again, it is right. Now what happens? If you see the current, which is the white arrow, and the magnetic field, they are parallel to each other. What happens then? Okay, let's do one thing. Let's write the expression. Let's write the expression. So the force is equal to, the expression now, I L cross B, right? If the two vectors L, length, right? The length of this conductor, which I've drawn along the x-axis, you can see, right? This is along the x-axis, the whole length. This length is along the x-axis parallel to B, right? So the what is the angle between L and B? What is the angle between length and B? 0 degree. They are parallel. Parallel means 0 degree, right? If the two vectors are parallel, what is the angle between them? 0 degree. If the two vectors are anti-parallel, which means one vector is in this direction, the other vector is in this direction, what is the angle? 180 degrees. Read the questions very carefully of this topic. The anti-parallel word will mean take angle as 180 degree. But in our case, we are taking parallel because in the situation which Dimpi saw, the current carrying conductor was parallel in the initial one. So I, L, B, magnitude into sine of 0. What is sine 0? Equal to 0. And this is what Dimpi saw, that the force experienced when the current carrying conductor is kept parallel to the magnetic field and the angle between them is 0. Parallel means 0 degree. The force is 0. Then what Dimpi saw? Then Dimpy did one thing. Dimpy kept the wire perpendicular to the magnetic field. So let me draw the wire perpendicular to the magnetic field now. So let's draw it. So this is perpendicular, right? You can see the angle here is 90 degree. This is the angle being referred to. Let's talk about the angle. What is the angle being referred to? So this is the angle I am referring to, right? So this is the angle. So you can see now I have drawn a 90 degree, right? This is the direction of the current. You can see the current is moving in this direction. I hope it is clear in your mind. Let me just darken this so that you can see the current carrying conductor, right? The current carrying conductor I have shifted for situation number 2, where the length and B are perpendicular to each other, right? So length vector and B vector are perpendicular to each other. And then let me draw that white current. So the current is moving in this particular direction. So that this is the direction of the current. What will be the expression now? What did Dimpy see? This is what Dimpy saw. Now the force experienced is given by I L cross B, right? This is the expression, a vector form. Let's write the magnitude of F now. What is the magnitude of F? Right, the magnitude of F. This was a vector form. This is the magnitude. This is the magnitude. The magnitude will be given by I L into magnitude of B into sine of 90, right? Because the angle is now this angle, right? This angle, 90 degree. Because the wire is kept now perpendicular. So B is along x-axis, the wire is along z-axis, right? This is the wire being referred to, which I am just darkening so that you can identify the wire. What is sine 90? When is sine maximum? Sine is maximum and theta is 90 degree. So the theta we read in the expression has become. So angle is very important in these questions. This angle. If you change this angle, the force on the current carrying conductor can be changed. So you kept the angle as 0 degree. There was no force. The angle between B and L. Then between B and L, you change the angle to 90 degree. The force which you get is the maximum force because sine is maximum at 90 degree. If you see a sine graph, what do you see? At 0 degree, it is minimum. Then it goes up at the highest point when theta is 90. When theta is 90, whatever is this y, right? This will become maximum. So the force is maximum at 90 degree. So if you keep on changing the angle of this L with the magnetic field, you will get different forces. This is the idea. Keep on changing, shift it to some other place. Let's shift it to this place, okay? Let us shift the wire to this place. So let's draw. I'm drawing the wire now, right? The wire is here. The wire, I'm drawing the wire here, right? So this is the wire. And again, I'm explaining you. I'm not giving you the answer. I've already given you the answer. My channel is known for explanation. So don't forget to subscribe. Don't miss on any question. All the questions will come in your examination. They can come in entrance examination. If the question is not same, at least you will see the concept was identical. There was no difference between what I taught. And some of my videos are very short. Don't worry, go and watch them. See the content, see the quality of the content. Don't worry about the presentation. I don't do comedy. I generally teach only. Okay. So this is the current here. Now what is the angle? If you were to find the angle, this is the angle, right? This is the angle now. Magnetic field is B and the angle is this. Looks like a large angle, could be 60-degree, right? Now what is the force? I am trying to tell you that if force is given, magnitude is given by B into L into I into, this is multiplication. This is not a vector product. This is the vector product, okay, when it is written. But when I'm writing magnitudes, it is not into sine theta, right? So force is actually a function of sine theta or depending on sine theta. I want to tell you this only, that if you draw a graph between force and theta, you keep on changing the theta, this is what you will find. The force value and the graph value, what will happen? What will happen is you will get this. If you keep changing, keep the length as the same, and you draw a graph between force and then you draw a graph between theta, okay, and you keep on changing, this is the graph you will get. This is very good, right? Because the force is proportional to sine theta. Keep on changing the angle, you will attain the maximum value at 180-degree, which is anti-parallel. The wire will be not in the positive z-axis but the minus z-axis on the other side. So the angle will become different, right? Or at least when we talk about minus 90-degree, that is what will happen. So this is 180-degree, which means the wire is now kept not here, but the wire is kept. I am drawing the diagram. The wire is kept in the opposite direction, right? In the minus x-axis. This is the direction of the conductor now. It changes, right? It changes. So I'm just darkening it so that you don't feel the confusion. So this is another alignment of the wire. The wire is making how much angle with the B? B is here. The wire length is here. This angle is 180-degree and this 180-degree is here, right? So the force and theta graph will look like this. One more additional point for your entrance examination or board examination. You can be asked this. I told you I will explain you the whole concept will be explained to you. I will not just give you the solution. I will tell you extra things which are not available anywhere. I hope this concept is getting clear in your mind and you're able to understand. This is the 90-degree which Dimpi saw. Dimpi also saw parallel situation, which was the 0-degree. No force, 0-degree. 90-degree angle between B and L, highest force. So the F max. Dimpi saw the F max here, right? So this is your F max. All right. Second part of the question was, what rule has been used? Okay, let's go to the state the rule used to find the direction of this force. Now let's talk about the rule. So the rule is a right hand rule. How do you know the force will go up? Right? How do you know this? Right? So there is a rule which is called as a right hand rule, which you have to use. Keep your palm like this. Right? Your fingers are pointing towards the B. Compare the diagram. Compare the diagram. Right? You can see the B in the hand and you can see the B, direction of B, right? You see this B and this direction of the B. Then see the direction of the current and the direction of the current. Then the force is upward, right? I hope you're able to understand. You have to use your right hand in such a way that the fingers point towards B. The thumb is always directed towards I. Again, I will tell you the problem. Do not point your uh, thumb towards I. This is another important point I'm going to tell you. This I have deliberately made this. Always point your thumb towards L. And now you will say, what is the difference? So let's say this is your current carrying conductor, right? This is your current carrying conductor. Now the current may be in some particular direction. Current may be in your particular direction. So the current is traveling like this, right? The current is traveling like this. Let me use some other color so that you can see this. So this is the way current is traveling inside this conductor. Okay. And so the current is traveling. Let me just enlarge it so that it is easily visible to you, right? So the current is traveling and going, right? But there is a problem. There is a length here. The small dl I told you, if you keep this conductor in a magnetic field, then how will you calculate? It will become very difficult, right? So what you do is that the small part of the conductor is taken, okay? The small part of the conductor, you draw tangent to this conductor. So I'm going to do what I'm going to do. I'm going to draw tangent at a certain point where I want to find the, so this is what I'm going to do. I am going to draw a tangent. Let me just bring it down so that it is easy for you to see this, right? And then let me select a color which is convenient, right? So let's select a color which is convenient and easy to see. Let's draw the tangent. So I'm drawing a tangent to this conductor. Look at this. So I'm drawing tangent at this point. This is the tangent. So do you see that there is a tangent being drawn to the wire? This tangent is the direction of the DL. Current can flow the way it has to, but don't worry about it. You can see the white arrows representing the current. But if you have to apply this law, the force has to be found out on a particular section of length DL. So the section I am considering here is a very small section, DL. This is the DL I am taking, right? The direction of DL, the direction of DL is found. If you have to find the direction of DL, there has to be a way. See, when it is a straight wire and a straight current, it is very simple. You can see the direction of the DL is same as that of the current, but in this case, it is not the case. You can make out, right? So how do you find the direction of DL? By making a tangent to the wire carrying the current. To the wire carrying the current. So if you're writing F is equal to I, and you're writing DL cross B, then DL, how do you find the direction of vector DL? Draw the tangent. I has no direction, mind you. You don't have to take direction of I. Always take the direction of L, right? Obviously, in a straight wire like this, you have a straight wire. Let me just draw a diagram. So this is a straight wire, right? There is no difficulty. Where is the difficulty? There is no difficulty at all, right? So you just straight away draw the wire and you have a current inside it. So finding the direction of the conductor, is very simple. It is in the same direction. So the length and the wire and the current are in the same direction, right? So this is your L, right? Let me just use some other color so that it is easy. This is your L length and this is your current. They're in the same direction. You have no problem at all. I and L are in the same direction. But look at this situation. In this situation, the current is continuously changing the direction, right? It is going. If you have to find, for example, direction of length DL here, right? What do? You pick up your scale, or what do? You draw a tangent to the wire, tangent. This is a tangent. This will give you the direction. And you can see the wire, which is a physical wire, carries the current, but it is not necessary that the current direction and the wire direction, DL direction, are same. DL direction is tangent. You have to draw tangent to that particular section. So that there is this subtle point which you must understand, right? I hope this is clear in your mind. From now, again, I'm giving you detailed explanation of the vector form. How do you arrive at DL direction? Additional point, if they ask you in the board examination, what is the direction of DL? The direction of DL is a tangent to the wire carrying the current at that point, right? Now let's go back. What we were studying, we were studying the direction. I hope the direction part is not very complicated for you. We were discussing this part, right? The thumb. So assume you, if this thumb is reversed, if you have a thumb, no, in the current direction is in the reverse direction. So assume that the current is in the reverse direction like this. Okay, let me just use some other color which is easy to see. Let's say the current direction changes. The current is in this direction, right? What will you make out? Since, see, in this particular diagram where you see, where you kept your hand like this, the direction of force is upwards. If the current direction is reversed, the force will be downwards now, right? The force will become a downward force. So always use this diagram to envisage scenarios, right? You can using this diagram imagine in your mind, if you now, for example, you change the direction of B. So I told you, you have inverted the direction of I, right? So I was here, so force became inverted, right? Force became inverted. Similarly, if you invert the direction of B, right? If you invert the direction of B, what happens? Keep your right hand, the finger directions in the direction of B now. As simple as that. Keep your current in this direction, whatever direction you see. Again, what will you find? That the force direction is inverted. So use this direction hand, use your hand, use your finger actually. I use fingers because I find them to be very simple. I use fingers. I don't use my complete hand. So if I were to use, I will, instead of using the whole hand, I will use only, one finger, my index finger as a B. So you always use this. It is very simple. Don't use your complete hand. Just use this one finger as a B. So invert your B, take your finger on the other side, keep your current, and the force will go down. You can easily make out because this is your finger which is showing you the direction of B, right? This is the finger. The current is in this direction. The current is in the direction of the thumb again, right? And now, and if you see, draw this diagram, your middle finger, right, which is the will go down toward the hand will look downwards. So this is your x-axis. This is your the minus x-axis. This is your z-axis. The current is not changed. I have just inverted the direction of B. B has got inverted. You will find your hand will now point downwards. The force will change. But if you memorize this, if F is kept like, if I is kept like this, B is kept like this, again I'm saying, do not use your hand, just use your index finger for B. Use your thumb, and you will find that the hand either looks up or looks down. If the hand is looking up, the force is up. Just adjust your index finger and thumb. Index finger for B, thumb for L. This is what you need to do, and you will get the direction of the force, right? So the diagram is not perfect. Obviously, this is not a thumb. Doesn't look like one. I have not drawn the whole hand. This is my index finger, okay? The index finger, and this is my thumb. So I hope this concept is clear in your mind as to how we decide the direction, and the rule is the right hand rule. You can go and watch a lot of videos. Do a search of right hand rule in my YouTube. I will give you links which you have to go and watch. There's some fantastic numericals which I have done, and you once you start, understanding them, the vector product video, the video that explains you, the how to find the direction, and extremely good questions. If you're preparing for JEE mains and NEET and board examination, some fantastic videos. Let's go back to the question on the values part, which is also a nice thing to learn through physics. So if you were a student and you have to answer what is the one situation which you demonstrated the value, so the which value is displayed and conveyed by grandfather as well as Dimpi. I think the value which is being conveyed is the value of flexibility. So we should be flexible, accommodative as per the circumstances. Both are trying to say the same thing. If you have to talk about a situation, I'm sure as a student you play in parks where there are a lot of elderly people like your grandfather doing walking. So a lot of grandfathers or grandmothers are walking, and you're playing cricket, and the ball or football, and the ball is continuously going towards them and hitting them. Maybe not hitting them, but at least obstructing them. Now, the old people are not able to walk properly and lose balance, and are generally they are very anxious. If they see a ball coming towards them at a very fast pace, they may become very anxious and they may lose their balance. So they may request you that can you play somewhere else. So you have to be flexible enough and say, okay, we will play somewhere else, and once they go away, then you can come back and start playing. What is this? This is a sign of living peacefully and happily. Both the people are happy. You go and play somewhere else. You be flexible, and towards your grandparents or people who are elderly. So this is an example where you demonstrate flexibility towards elderly people. I will not go in details of this. I'm sure you're mature. You understand all of this. My whole idea of this video was to combine and as to and give you how to find out that effect, which is the actually the force experienced by a current carrying conductor on due to a external magnetic field. And I explain you the rule, and I also discuss this value question. So I hope this made sense to you, and now you can answer any question and every question pertaining to the force being experienced by a current carrying conductor in a external magnetic field, and use the theta, which is very, very important. Don't forget to subscribe to this channel. You will find some extremely good numericals sitting at the comfort of your home. The level of teaching is even better than classroom. No one in the classroom also will teach you this, and you will realize when you do the comparison, this level of teaching is not even available. The explanation part, at least, is not available in the classroom. Thank you very much, and wait for my next video now.